We will begin with an example number 1 by proving that a root exists in a given interval and then apply the bisection method step by step. By the end of this video, you will be able to implement this technique confidently and understand its practical applications. So let's get started. We are given with the example number 1, and we have a question that we need to show that we have a function that is x cubed plus 4x squared minus 10, and this is a nonlinear equation, has a root in this interval, and use the bisection method to approximate to the root that is accurate to at least within 10 raised to the power minus 3. So 10 raised to the power minus 3 mean we need to check the accuracy till 3 decimal places, that is after decimal we have a 3-digit accuracy. So let's begin with the solution, step-by-step solution. Okay, firstly we are going to compute the function values at the given interval, at the starting point and at the end point, that is the 1 point that is at 1 and at 2. So when we put 1 into our function, we will get 1 cube plus 4, 1 square minus 10, and when we solve it, we will get negative of 5, that is less than 0. Now we are going to substitute 2 into the function, and we will get 2 raised to cube plus 4, 2 square minus 10, and we will get a value 14 that is greater than 0. So since f of 1 and the f of 2, their product is less than 0, so a root exists in the interval that is 1 comma 2, right? And when we substitute 1 into the function, we will get a negative value, and when we substitute 2 into the function, we will get a positive value. So now we are going to start with the by applying the bisection method, and we are going to perform the iteration. So first iteration, x1 is equals to 1 plus 2 divided by 2. So the answer would be 1.5. Now we are going to substitute 1.5 back into the function in order to evaluate the sign. So 1.5 raised to cube plus 4 1.5 raised to square minus 10. So the answer would be 2.375. It means that greater than 0. Since f of 1.5 is greater than 0, so root lies between negative side would remain same, that is 1, and we update our result to the positive side, that is 2, so 2 will be replaced from 1.5. So our new updated interval is 1 to 1.5. Next we are going to proceed toward the iteration 2. So second iteration, now we are going to find out our second approximate root with the help of the first one. So x2 is equals to 1 plus 1.5 divided by 2. So the answer would be 1.25. Now we substitute into the function in order to examine the sign. So 1.25 raised to cube plus 4 1.5 raised to square minus 10. So the answer would be negative of 1.7968. So since f of 1.25 is less than 0, so the root lies between, we need to update our interval, so the positive side will remain same, and we need to update our result on the negative side, that is 1.25 comma 1.5 remain same. Now we are going to go for the third iteration. So for the third iteration, we need to find out x3, that is equals to 1.25 plus 1.5 divided by 2. So the answer would be 1.375, and we need to put it in a function in order to examine the sign. So the answer would be, we need to substitute into the function, and our function is 1.375 raised to cube plus 4 1.375 raised to square minus 10. So that is equals to 0.1621. Since f of 1.375 is greater than 0, so root lies between we need to update on a positive side. So our new interval would be 1.25 remains same, and we need to update on a positive side, so it becomes 1.375. Now we proceed toward the fourth iteration. So x4 is equals to 1.25 plus 1.375 divided by 2. So the answer would be 1.3125. Now we need to substitute in a function 1.3125. So that is 1.3125 raised to cube plus 4 1.3125 raised to square minus 10. So when we solve it, we will get the result negative of 0.84835. So that is less than 0, since f of 1.3125 is less than 0. So root lies between, we need to update our interval on the negative side. So we need to replace 1.25 with 1.3125, and our positive side would remain same. Now we need to, okay, if you look at the results of the intervals, so we will find the accuracy till 1 decimal places. But we need to achieve 10 raised to the power minus 3, which means that we need to achieve 0.0001. So we need to go for more iterations. So let's go for the fifth iteration. So x5, that is equals to 1.3125 plus 1.375 divided by 2. And when you solve it, you will get 1.34375. Now we substitute the value into a function 1.34375 in order to examine the sign. So 375 raised to cube plus 4 into 34375 raised to square minus 10, and we will get negative of 0.31374, that is less than 0. Since f of 1.34375 is less than 0, so root lies between. So we need to update our interval on the negative side. So the updated is, we need to change it 1.34375, and the positive side will remain, that is 1.375. Okay, we need to go for the more iterations. So the sixth iteration. So x6, that is equals to 1.34375 1.375 plus 1.375 divided by 2. So when we solve it, we will get the result 1.359375. Now we substitute back into the function. So 1.359375 raised to cube plus 4 1.359375 raised to square minus 10, and we will get the result negative of 0.096408. Since f of 1.359375 is less than 0, so root lies between. So we need to update our interval on the negative side. So it should be 1.359375 and the positive side will remain same. Now we go for the next iteration, that is our seventh. So in the seventh iteration, we have x7 that is equals to 1.359375 plus 1.375 divided by 2. So when we solve it, we will get 1.36717875. Now we substitute into a function in order to examine the sign, and we will get 1.36717875 raised to cube plus 4 1.36717875 raised to square minus 10. So when we simplify it, we will get 0.03236. So since the value of the function is positive, 3671875 is greater than 0. So our updated interval is, so this is a positive, so we need to update on a positive side and negative side would remain same, that is 3593765, and we are going to update our positive side with 1.36718775. Now if we look at this, we will get accuracy till 1 decimal places still, so we need to go for more iterations. So let's proceed to the 8th iteration. So x8 is equals to 1.359375 plus 1.36717875 divided by 2, and we will get the results 1.36328125. Now we need to substitute into a function 1.36328125. So 1.36328125 raised to cube plus 4 1.36328125 raised to square minus 10, and when we solve it, we will get negative of 0.032147. Since the value is negative, I may write x of 8, oh, not x of 8, it is 1.36328125 is less than 0. So the root lies between, so we need to update on a negative side, so value will be value is updated to 1.363 28125, comma 1.3671875. The positive side will remain same. Now we need to, okay, if we look at the results, we will achieve the accuracy to 2 decimal places. So it's mean that in order to achieve the accuracy till 3 decimal places, we need to go for more iterations. So let's proceed to the ninth iteration. So x9, that is equals to 1.36328125 plus 1.3671875 divided by 2. And we will get the result 1.365234375. Now we substitute back into the function. So 1.365234375 raised to cube plus 4 1.365234375 raised to square minus 10. And after solving, we will get the results 0.4 times 0, 7, 2. So it's mean that since f of 1.365234375 is greater than 0, so root lies between this interval. So we need to update the interval on the positive side, so the negative side would remain same, 363282125, and we need to update 1.365234375. Still the accuracy is still 2 decimal places, so we need to go for more iterations. So let's go to 10th iteration. So x10, that is equals to 1.36328125 plus 1.365234375 divided by 2. So after solving, we will get the result 1.364257813. Now we substitute into a function 4257813. So we will get 1.364257813 raised to cube plus 4 1.364257813 raised to square minus 10. So when we solve it, we will get the result negative of 0.01605, since function 1.364257813, that is less than 0. So root lies between. So we need to update our result on the negative side of the interval. So 1.364257813, and the positive side would remain same to 1.365234375. Now we go for the 11th iteration, because still we achieve the accuracy to 2 decimal places. So we need to go for more iterations. So 11th iteration. So x11, that is equals to 1.364257813 plus 1.365234375 divided by 2. And when we solve it, we get the results 1.36 4746094. We need to substitute in a function. So 1.364746094 raised to cube plus 4, 1.364746094 raised to square minus 10. So when we solve it, we will get negative of 0.00799. Since f of x11 is less than 0, so the root lies between. So we need to update the interval on the negative side. It should be 1.364746094 and the positive side will remain same, 234375. Yes, so still we didn't achieve the accuracy to three decimal places, so we need to go for more iterations. So let's proceed to the 12th iteration. So x12, that is equals to 1.364746094 plus 1.365234375 divided by 2. And after solving, we will get the results 1.364990235. Now we substitute in a function. So 1.364990235, that is equals to 1.364990235 whole cube plus 4, 1.364990235 raised to square minus 10, and when we solve it and simplify it, we will get the results negative of 0.00396. So f of x raised to 12 since less than 0, so the root lies between. We need to update on the negative side. So 1.364990235 is the updated side, and the previous would be unchanged, the positive side, 34375. Okay, still we didn't achieve the accuracy. So still we have the accuracy to 2 decimal places. So it's mean that we need to go for more iteration. So let's proceed to the 13th iteration. So x13, that is equals to 1.364990235 plus 1.365234375 divided by 2, and we will get 1.365112305. So we substitute back into the function in order to examine the sign. So we have 1.365112305 raised to cube plus 4, 1.365112305 raised to square minus 10. When we simplify it, we will get negative of 0.00194. So the value is negative since f of x13 is less than 0. So the root lies between. So we need to update our interval on the negative side. So 1.365112305. Sorry, it's comma. And we need to use the previous positive side. 2, 3, 4, 3, 7, 5. So if we look at the results, so we achieved the accuracy till 3 decimal places. We got 1.365, and here we also have 1.365. So let's find out the absolute error in order to confirm the accuracy. So we are going to find out the error, that is our absolute error, or we just simply write absolute error. So that is equals to 1.365234375 minus this value, that is 1.365112305. So when we subtract it, we will get 0.000012207. So we achieved the accuracy till 3 decimal places, because the requirement of the question is 10 raised to the power minus 3, which means we need to achieve 0.0001. So we achieved the accuracy after 13th iteration, and the basic interval we are given with is 1, 2. And that's how we solve this problem using a bisection method. I hope this step-by-step explanation make things clearer for you. If you found this helpful, don't forget to like, share, and subscribe to the channel for more numerical analysis tutorials. If you have any questions or want me to cover a specific topic, drop a comment below. I would love to hear from you. Thanks for watching, and I will see you soon in the next video. Keep learning and stay curious. Take care.